Hello everyone. So today we'll discuss some of the questions from the week 7 assignment of the course Introduction to Machine Learning by NPTEL. Okay. So here the question number 1, which of the following statements regarding the evaluation of machine learning models are true? So a model with lower training loss will perform better on a validation data set. That is false. Okay. A model with a higher training accuracy will perform better on a validation data set. So that is also not necessarily correct. So this is false again. The train and validation data sets can be drawn from different distributions. So again we need to draw both train and validation data set from the same distribution only. So it is also wrong. The train and validation data sets must accurately represent the real distribution of the data. So this last option, this is the correct option. Then the second question, suppose we have a classification data set comprising of two classes A and B with 240 samples respectively. Okay, so if I take the ratio of the data set A and B it is 240, right? So which is nothing but 0 0 10 5:1. Okay, suppose we use stratified sampling to split the data into train and test set. Which of the following train test splits would be appropriate? Now here if we need to use stratified sampling, then after sampling, the ratio of the classes A and B, that should be maintained. The ratio is 5:1. So if there are 5 samples from A, then in the for the B class there should be 1 sample. Okay, so that ratio should always be maintained if it is a stratified sampling. If it is a plain sampling, then this ratio need not to be maintained. Okay, now what are the options? The first option, the train in the train set, A class is having 50 samples, whereas B class is having 10 samples. So here we can see that the 5 no, the ratio is not maintained, right? The ratio here is 5:1. So the ratio is maintained here, right? Then in the test sample, what we have, again 150:30. Yes, so here that ratio 3:5. Yes, that ratio is also maintained here, right? 5:1 ratio is maintained here. Okay, we'll see forward what are the other options. The second option is having 50 sample from A and 30 sample from B, so that 5:1 ratio is not maintained. The ratio is here 5:3, whereas in the test sample as well, the ratio here is 15:1. Okay, so that ratio is not maintained. Then the third option, A is having 150 sample and B is having 30 sample. So here as well 0 0 will go cancel out, then 3 5s are 15, right? So 5:1, that ratio is maintained. And in the test set as well 5:50:10, which is equal to 5:1. So that ratio is maintained. So the option A as well as option C are the probable answers. Then let us see option D, 150:10. So that means it is 15:1. The ratio is not maintained in that train as well as in the test set. Okay, now out of option A and B, both are having maintained that ratio of 5:1, but out of this A and B C option, we will prefer option C as the correct answer, because generally it is a good practice that we need to use the number of samples, okay, the number of samples in train in training the data set should be always greater than the number of sample in the test data set. Okay, so this is a normal practice, a standard practice that we use while training a machine learning model. So here, since the total number of samples in the train set is greater than the sample used in the test set, so the option C will be the correct answer. Then in option question number 3, suppose we are performing cross validation on a multi-class classification data set, correct, with n data points. So data set is having n number of data points. Which of following statements are correct? In k-fold cross validation, we train k minus 1 different models and evaluate them on the same test set. So this option is not correct, because in k-fold cross validation we train k number of models only, okay, and we evaluate them on different test sets, okay. So this is not correct. Then second option, in k-fold cross validation we train k different models, correct, and evaluate them on different test set, that is also correct. So option B is one correct option. Then the third option, in k-fold cross validation each fold should have a class wise proportion similar to the given data set. Generally this particular definition, that each fold should have a class wise proportion similar to the given data set, this is correct for k-fold cross validation with stratified sampling, okay, stratified sampling. So there is one modified or advanced version of k-fold cross validation which is called stratified k-fold cross validation. So there this proportion of class wise proportion which is there in the data set should also be maintained in the cross validation, the different groups of the cross validations, okay, or different folds of the cross validation. But in a plain k-fold cross validation this need not to be maintained, okay. And the question that is given, it is on a plain cross validation, it is not a stratified cross validation, okay. So this option is not correct here. Then the last option, in leave one out cross validation we train n different models, that is correct, using n minus 1 data sets data points for training each model. Yes, that is correct. In leave one out cross validation, this is a extreme type of actually k-fold cross validation, where for training we use, if the total number of data points are n, we use n minus 1 number of samples, whereas for testing we use the left one, the last one, okay. That is for iteration 1, okay. Then we will keep on running these iterations for n different models. This is for the first model, okay. For the second model, then we'll take n minus 1 training sample only, but for the first iteration whatever we have left out for test, that one will include in the training set of the second iteration, okay. And one will leave out, okay, that will be for the test. So in leave one out cross validation only one sample is used for testing, okay, whereas in a k-fold cross validation there will be one entire fold or one set of test test set will be there, group will be there, where number of samples will be there, okay, more than one. So the last option, that is also correct. In leave one out we train n different models and n minus 1 data points are used for training each model, okay. Then moving forward, the question number 4. So here for a binary classification problem we train classifiers and evaluate them to obtain confusion matrices in the following format. So here in the row actual positive numbers and actual negative numbers of the data points are given, and in column wise only the predicted values are given, okay. So if we uh, fill this particular confusion matrix means uh, actual positive value which is predicted as positive, it is known as true positive. Okay, then actual positive value which is predicted as negative value, that is called what? False negative. The value is actually positive, but it has been predicted as negative by the machine learning model. Okay, so it is false negative. Then actually the value is negative but predicted as positive by the model, so it is known as false positive. Then actually the value is negative and also predicted as positive, which is known as true negative. Okay, so now there are four classifiers are there. Okay, classifier number 1, 2, 3 and 4. All these four classifiers, after running on some given data set, okay, for a binary classification, these are the statistics of true positive, false negative, false positive and true negative by all those four different classifiers. Now we need to find out which classifier uh, is giving me maximum recall value. Okay, so that I can choose that one for maximizing the recall value. Okay, so now for that what we need to know, we need to know the definition of recall. So recall definition is what? Recall is true positive upon true positive plus false negative. So the first row, how many are positively classified? Okay, out of total all the positive values, how many are predicted as positive out of the total actual positive? Okay, that this particular definition signifies this, that only. It is also called true positive rate. Okay, so here for the first one, if I calculate the recall for the first one, then the true positive is what? 4 upon true positive, that is 4 plus false negative, which is this value, right? Row number 1 but the column number 2, that is 6, which is equal to 4 by 10. Similarly for the second classifier, the recall value is what? 8 by 10. Yes, for the third classifier, recall value is 5 by 10. For the fourth classifier, the recall value is 7 by 13. Correct? Sorry, 7 by 10. Okay, so since the denominator is 10 for all, we can very easily compare all these value and we can find out that this classifier is giving me what? Maximum recall value. So that will be the correct option. Then moving forward for the second question. Okay, for the second question, for the confusion matrices described in question number 4, here also confusion matrices, whatever confusion matrices is represented here, the values that is represented, that is in this pattern only. Okay, which of the following classifiers should be chosen to minimize the false positive rate? Okay, so again now we have to know what is the definition of false positive rate or FPR. False positive rate is false positive in the numerator, then false positive plus true negative in the denominator. Okay, so that is called false positive rate, and we have to find out which of this classifier is giving me minimum false positive rate. Okay, so the first one, false positive is this one, row number 2 and column number 1. So value is 6 divided by 6 plus true negative, the second row, right? That is 84. Yes, so the value here is 6 upon 90. So we can understand that the denominator is nothing but the second row, right? So the denominator will be same for all the values, all the classifiers. So for the second one, numerator is 13 false positive, yes, upon 13 plus 77, which is 90. Then the option C here 2 in the numerator upon 2 plus 88, which is 90 again. Then the last option 4 upon 4 plus 86, which is 90. Yes. So since the denominator is same for all the all the values, we can easily now compare which one is the minimum value. So we can understand that 2 by 90 is the minimum out of all these four values, right? So here the correct option is C. Question number 5, correct option is C. Then again moving forward, here for the confusion matrix, again for the same confusion matrix, the question is which of the following classifier should be chosen to maximize the precision. Now we need to understand the definition of precision. What is the definition of precision? It is true positive upon true positive plus false positive. Yes. So if we see the here the first column, yes, true positive upon true positive plus false positive. So this is called precision, right? So if we now see this precision value for each and every classifier, it will be 4 divided by the first column, right? Let me again verify. True positive, then the second row, first column is the false positive. So we have to concentrate on first column. 4 plus 6, correct, which is equal to 4 by 10, which is equal to 0.40. So here we are taking the decimal value for comparison, because you can see that the first column for each and every classifier is different, right? The denominator will not be same. Then for the second one, 8 upon 8 plus 13, which is equal to 8 divided by 21. Okay, so this comes as question number 6. 8 upon 21 is 0.38. Okay, then for the third classifier, it is 1 upon 1 plus 2, which is equal to 1 by 3, which is equal to 0.33. Yes, 33%. Then the last one, 10 upon 10 plus 4, which is 10 by 14 equal to 0. This value is big, right? 0.71. So I need to maximize the precision value. That means I need to find out which one classifier is giving me the highest precision value. So that is the last one, 0.71, right? So the correct option is D. Then for the last question, for the confusion matrices described in question number 4, which of the following classifiers should be chosen to maximize the F1 score? Okay, again we need to understand what is the definition of F1 score. So the definition of F1 score, if we break it, it comes down as twice of true positive upon twice of true positive plus false positive plus false negative, right? So if we cross check with the confusion matrix, true positive is this one, then on the denominator I have Fp and Fn, right? So diagonal values Fp Fn also added with twice of true positive, right? So I need to add all those values in the denominator. So the first one will be true twice of true positive, that is 2 into 4, that is 8, upon twice of true positive, that is 8, plus the diagonal values 6 plus 6, okay, which is equal to 8 divided by 20, which is equal to 0.40. Then for the second one, twice of TP, that means 8 into 2, that is 16, then 16 plus 2 plus 3, which is equal to 16, correct, then 5, right? So 21, 16 upon 21, which is slightly like not slightly, but it's a much bigger value. Denominator is 21 and double of the numerator of the first option, so it comes down as 0.76. Then the third option, 1 is to 2, 2 TP, 2 plus 9, which is equal to 2 divided by 9, 10, 11, 12, 13, right? 2 by 13 which is equal to 0.15. Yes, and the last one, twice of 10, that is 20 divided by 20 plus 4 plus 0, okay, which is equal to 20 by 24. I think this is the biggest value, 20 by 24, which is 0.83. okay, so as I need to maximize the F1 score, I need to find out which is the biggest value, which is the largest value. So the option number D, right, that comes as a highest or maximum F1 score. So 7 option, correct option is D. Then what about the question number 8? Which of the following statements regarding boosting is are correct? So boosting is an ensemble example of ensemble method. Yes, correct. Boosting assigns equal weights to the predictions of all the weak classifier. No, this is not correct. Boosting assigns higher weight values to the wrong predictions or mistakes of of the current weak classifier, and for the next weak classifier, those weighted all those mistakes that is done by the current classifier, okay, for those data point the weight value will be maximum, the weight value will be higher value, okay, than the correct prediction value. So the second option is wrong. Boosting may assign unequal weights to the predictions of all the, yes, correct, that is what it is correct. The individual classifier in boosting can be trained parallelly. No, this is not correct. Boosting is a is one ensemble technique where the classifiers are sequentially trained, okay. The output of the next classifier will depend on the output of the previous classifier. Once the previous classifier is trained and their mistakes are highlighted by giving higher weight values, and on those training data, then the next week classifier will be trained. So it is done one after another. So individual classifier and boosting cannot be trained parallelly. Yes, that is the correct option. So for question number 8, A, C and E is the correct answer, are the correct answers. Then question number 9, which of the following statements about bagging are correct? Okay, so bagging is an example of ensemble technique, correct. The individual classifiers in bagging can be trained in parallel. Yes, that is correct. In case of bagging, all the individual classifier can be trained parallelly, because they will be trained on different data sets. They will be trained on data sets which are generated by doing sampling on the original data set. Okay, sampling with replacement, actually it is. Training sets are constructed from the original. So B option is also correct for question number 9. Training sets are constructed from the original dataset by sampling with replacement. Yes, that is what I was telling. Training sets for a bagging technique, these are constructed from the original dataset by sampling with replacement. Means once this original dataset is there, okay, so when I will draw samples for the newly created data sets, whatever sample I will draw for D1, okay, that sample will again be returned, like it will be from the population of this D data set, that same sample will again be replicated, like it will be returned again to the population before I do the new sample selection. Okay, so means if suppose there are some samples, right, sample 1, sample 2, okay, not there are some data points like 1, 2, 3, okay, 4, these are some data samples. If I draw data point 1 for the D1, it will be there in the D1. Also it will before drawing the sample for D2, okay, that data point will again be there in that population. So this one can again be selected for D1, D2 also. Even for while choosing, suppose here I need to choose 2 data point for D1. Okay, so first data point I have chosen 1. Second time, because this data point will be there in the population again, this can again be chosen in D1. So the second data point may also come as 1 only, 1 1. Okay, so this is called sampling with replacement, and bagging follows that. So question number 9, A, B, C all are correct till now. Let's see option D. Training sets are constructed from the original dataset by sampling without, no, this is not correct. In case of without replacement, once we draw the sample 1, okay, then it will not be added back to the population. Bagging increases the variance of an unstable classifier. No, bagging actually decreases the variance after when we take the final classification, then it decreases the variance actually. So that is also wrong. Then question number 10, which of the following statement about ensemble methods are correct? So here question, ensemble aggregation methods like bagging aim to reduce overfitting and variance. This, yes, that is correct. Committee missions may consist of different types of classifier. Yes, committee missions are what? They are there are static committee missions, dynamic committee missions. So these are nothing but the ensemble methods only, the random forest and bagging, okay, those are static committee machines. Okay, whereas there are dynamic committee machines are also there, like boosting technique, okay, or stacking, okay, those are called dynamic committee machines. Whereas all the random forest in bagging technique, when we use majority voting and all, those are static committee machines. And all these classifier that are used, those can be different classifiers. Okay, so this option here, the option number B is correct as well. Weak learners are models that perform slightly worse than random guessing. Okay, so weak learners are models that perform slightly worse than random guessing. No, this is not correct. It should give higher performance than random guessing. Then the last option, stacking involves training multiple models and stacking involves training multiple models, yes, and stacking their prediction into new training data. Yes, stacking involves training multiple models, for example decision tree, neural network. Okay, KNN classifiers or different models will train, and their prediction and stacking their prediction into new training data. And finally we try to find out the best predictions that is done by all those different models. Okay, so yes, this also is a correct option. So these are the answers for this assignment 7, week 7 of introduction to machine learning, and all these questions are related to the different ensemble techniques, and mostly on how we can evaluate or how we can measure the performance of the different machine learning models on that. Okay, so if there is any doubt, you can post in the comment section. Thank you.